want this industry to perform its duties. So we have an existing road. Our penstock came in at a lower level here. We've done our clearing. Now we've benched out and we're putting in our trenching and laying out our pipe. This is about a 10-foot diameter pipe. It's all backfilled now, and we're just doing the final touches. And there's a reclaimed right of way with the drainage path across, all the reclamation work done, and that's total design sequence, including the rehabilitation. Took about 4 or 5 months to do that piece of work. Here's the powerhouse, and if we have time at the end here, I've got a time-lapse photography of this powerhouse being constructed from top to bottom. It took about 3.5 months to build that. And you can see the Manicom River flowing by, lowering in the turbines. In this case, the double Francis turbine, which is 2 Francis runners operating within the same scroll case, discharging in 2 different directions. A unique design that we use a lot in Canada because of our high flow range variability. Put in our bifurcation for the penstock pipe. That piece weighs about 80 tons. And we get into the powerhouse itself with 2 turbines with 4 runners, and that gives us a very broad range of high efficiency operation for the facility. And there's your powerhouse nestled into the bottom of the rock area, and this is where the end of the rock canyon ends and the beginning of the Squamish Valley, and this is where we're discharging right into the Manicom River. And there we are, fully connected. And I mentioned earlier the bypass system. This pipe right here is connected to the bifurcated off the penstock pipe, and it is able to discharge and dissipate 20 megawatts of energy in 9 seconds on load rejection of the unit, so that we have no interruption of flow and no change to the water regime within the river system. And we invented a new way of doing this. These type of valves that are used for this have been in use in Canada and around the world for over 100 years. And we invented a way of taking the energy dissipation capability of that from 45% up to 95% with about a $30,000 modification. And we did some of the laboratory work on that in Vancouver as well as in Edmonton. I wish I could have done it here, but now we can because we have a new water lab in the basement that we could do that in. So the next project I want to talk about is the Clohome project. It's actually 2 hydro projects we built simultaneously. It's on the Sunshine Coast up near Seashore. If anyone knows that area. And what's unique about this one is that there's no road access. It was all built by ocean barge, and or we flew in materials as well. So we begin with bringing in our ocean barges from Vancouver and area. Bringing in our camp facilities. We built a 150-man camp in an old gravel pit in the area. This is an area that's been logged for over 80 years now, and so there was a road network, but no access to that road network other than by ship. Building our upper intake works, an existing alluvial fan slide area actually, and we used a number of different materials. This is ductile iron pipe that was made in Tennessee and shipped up by rail, loaded onto barges, and then brought into the site. And they're just stockpiled, and it was one of the few applications where we used this type of pipe for this type of application. Putting it in, backfilling, usual processes. On the case of the lower plant, we used steel from Korea, and this was made as raw pipe in Korea and then coated in Vancouver and then put on the ship and brought up to our site. As you can see, it's a lot like the usual pipelining systems, but our pipes are a little bit bigger than the oil and gas pipelines you see around. Use the same kind of equipment, same kind of techniques, but our bends cost in the order of $40,000 a bend, so you try to limit the number of times you bend the pipe. But the mountain is the mountain, and And in this case, we're in an alluvial fan again with high groundwater, so we had to have a high pipe design to keep from interrupting the groundwater flow. And you can see that here we are in a nearly completed state. This all gets reclaimed afterwards, but there's a couple bends in that pipe as you wander down the mountainside. We also have to cross the creek at the intake location, which was no small challenge. You can't quite get a full appreciation for the steepness and the elevations that you're talking to, but most people would think that you're standing on the edge of a sheer cliff where we're doing some of this engineering work. And then we are in almost complete the crossing system. This is an intake, and I won't go through too many details here, but there's at least 20 major hazards at this intake location. Some of the major ones being flood, but the biggest one is the rock fall. There's a mountain peak that's way, way up here that during construction, the early part of the construction, we had 2 boulders come down the size of pickup trucks. We thought that was kind of a dangerous place to be. So we had to build the largest rock fall fence in Canada for this project. And here it is here, you can just see the mesh. Here's some rock that just fell 3 weeks ago. 18 tons worth of rock came down from over 1,000 meters above us. It sheared off a path that you can see all the way through the forest coming down to us. And you can see our intake works is right here. And our client wouldn't be too happy if that ended up in the middle of his gate works. So you can see the size of this boulder, it's not too small. And this system is actually a system embedded in Switzerland and Germany. And it's amazing. This rock is actually about 50% larger than it was designed for, and it still worked well. So now a little bit about current projects, and this is the Long Lake project. This is one of the highest head hydro projects in North America. We're at 778 meters in vertical elevation difference between the pond level and where the powerhouse is. It's in a mine that was built back at the turn of the century that actually started the Toronto Stock Exchange, one of the 3 mines, called the Premier Mine. It's a gold, copper, silver mine, and this mine's been opened and closed about 6 times in its life. There's huge tailings facilities full of arsenic and things all in this area. The area is littered with mine openings, strip mine, as well as underground mining. And what we're doing is capitalizing on the abandoned works. And there's an abandoned dam at the top. We're right at the bottom of the Alaska Panhandle, and so we actually have to go through the United States to come back into Canada to get to this site. And we had to go through international boundary water approvals because the river flows both into Canada and the US and then back into the Canada before it enters into the ocean. So a lot of regulatory challenges and a lot of issues relative to site use. This site was originally offered a PPA under the commercial generation policy in British Columbia, which allowed in the fence generation between, and it was a joint venture between the existing mining company and the hydro developer, but the mining company abandoned the mine partway through the process, so that it had to be renegotiated on a power purchasing contract as a standalone hydro facility. This is the fuel for that area. This is the Salmon Glacier. If you guys ever wanted to see a spectacular part of the world, it's not well known. I encourage you to go up to Stewart, BC, and Hydro, Alaska. Some of the best looking terrain you've ever seen in your life. This is the abandoned dam that was actually blown up by the US Marines in Canada. Little known fact. And it was determined to be a hazard to the US, which it wasn't. There's perceptions at the time. And so this actually, you can see this old log building, and this was actually built back in 1910. And it was only blown up back in 1992. And now we're rebuilding a new dam in the exact same location in 2011 or 12. So here's the powerhouse location right in this location here. These are underground mine workings that are sort of working up actively. You see a tailings pond down here for this mine working, but the large tailings dams up here are where all the arsenic is. is from the original mining activities.